Ah, you clicked on the link.
Okay. No, now it's good. Okay, so welcome back. Our next speaker is David Larraguivel Carrillo, and he will give us a user guide for the knots-quivers correspondence.
Thank you, everyone. So, as well, thank you for the organizers. I highly appreciate that the talks start at 11. That's wonderful. We should keep it this way more often.
Yeah, I'm happy that there is a sign of support.
I'm up for that. Very good. So, without further ado, I want to give you a good feeling of what the knots-quivers correspondence is without going too much into the technical details, but as a preacher, more through examples. So I don't expect anyone to be necessarily familiar with this topic. So I'll start from the basics. So knot theory has provided many tools to study low-dimensional topology, quantum field theory, and so more. But there are not invariants that we heard in today's lectures that are not just difficult to compute because they get so convoluted, but even difficult to define precisely and to have a systematic way of computing them. So in this context, this is where the knots-quivers correspondence attempts to make a breakthrough or to enhance our methodology for studying knots. So yes, in a nutshell, you take knot invariants and you repack them in terms of knot quiver data. I'll make everything more precise in a moment. But instead of carrying your infinite knot sequences of invariants, now you just need to carry in a bag your matrix and some homology generators, which is much easier to find, much more visually interactive, and who knows, perhaps even much more geometrically rich than simple polynomials. So I'll start with a tale of two theories. So on one side, we have the Chern-Simons theory on S3. We put a knot, physicists call it a Wilson loop. So what we do then is we can compute the Homology polynomial using the well-known scaling relations, essentially taking into account the crossings. And this normalization, we use the reduced normalization just to take into account, and we work with q to the power 1/2 for those who must know. Then we move on, and we start with Chern-Simons action. From here, if you compute the holonomies around the knot or the Wilson loop, which are essentially computing these traces, so this path order traces of these exponentials of this action on S3, then you get the so-called colored Homology polynomials, colored by symmetric representations R, which we already heard today very nicely introduced. So this is one of the main objects that you need to keep in mind. So this is the generating series for the colored Homology polynomials. This is the Q-Poch hammer used for our normalization convention, so reduced normalization, sorry. Okay, and on the other side of this tale of two series is the quiver. So a quiver is just a set of vertices and arrows between vertices, as simple as that. It also sometimes goes by the name of multigraph, but for us, the main idea is that having these nodes or vertices and edges between them, or more precisely arrows, sorry, we can construct an adjacency matrices representing this graph. For us and the rest of the talk, we will only be concerned about adjacency matrices which are integer valued and symmetric, because those are the ones that appear in this knots-quivers correspondence. So quiver representations are when we associate vector spaces and linear maps between vector spaces or homomorphisms to each vertex of the quiver, then the question in quiver representation theory is how to classify these maps. So this question posed by Pedram some moments ago, the combinatorial interpretation of this motivic VT invariants associated to the symmetric quiver can be understood as the Betti numbers of the moduli space of semi-simple representations of Q, or as the Chow-Betti numbers of the moduli space of all simple representations. You don't really need to know all that. It's a mouthful, but the important punchline here is this second formula. So for a symmetric quiver, the generating series of these Donaldson-Thomas invariants takes this simple form. So here is the quiver matrix, symmetric. So this is just an inner product with these. These are the dimensions of these vector spaces. So we call this the dimension vector. We sum all the way to infinity. Here we have also some Kupo-Hammer factors. And these are the formal variables that Pietro was talking about moments ago. It happens, and this is an important fact related to the LMOV invariants or Donaldson-Thomas invariants, that this series can be rewritten as in an infinite product form, where the exponents here are proven, at least for symmetric quivers, using homology arguments, that these are positive integers if you take into account this weight factor. So far, any questions? Now you're experts on it? Very good. So the physical idea, what Pietro was transmitting in his talk, can be summarized in this slide. So on one side, you have the deformed conifold, you have a knot, and you have a Lagrangian brain ending on it. Here you have n branes, and there is a geometric transition. So what we were calling some sort of large n duality, not precisely, but for us that's enough. And on this other side, you have the resolved conifold, which essentially relates the deforming complex parameters intersecting S3 with the blowing up of the singularity on S2. So colloquially speaking, you have an S3 sphere, you shrink it, and then you inflate it back into a S2 sphere. That's geometrically what's going on. And on one side, you have a 3D n equal 2 supersymmetric gauge theory, and on the other side, you have Chern-Simons theory. So that's the idea of these two theories and the duality, that knot invariants are related to BPS numbers of this quiver representation Donaldson-Thomas invariants. So to sum up, on one side, you can take the infrared limit, or just some limit of this theory. You get your famous Chern-Simons. You can compute the colored Humphrey-Petit polynomials on this side, and you can compute the Donaldson-Thomas quiver generating series from the data of this side. And the whole idea of the knots-quivers correspondence in just one equation is this. So the generating series of Humphrey-Petit polynomials can be related to the generating series of quiver Donaldson-Thomas invariants after a suitable change of variables. And the simplest example, which we have already seen 2 times today, so I hope you memorize it, is the trefoil knot can be associated to this simple 3-node quiver. So it's the simplest non-trivial example. Just a brief word about Labastida, Marino, Oguri, Baffa invariants. So another reason why the knots-quivers correspondence is important is because Donaldson-Thomas invariants are proven to be integers, whereas here it was a long-standing conjecture, and it still is for all knots, to prove that these exponents are positive integers, or essentially integers with certain weights associated to them. So in this form, if you prove that a knot has a corresponding quiver description, then it automatically proves that the LMOV invariants are integers. So that's one of the main achievements or successes of this knots-quivers correspondence. So one way to prove the full Lavassida-Waffa LMOV conjecture would be to prove knots-quivers correspondence in generality, which is easier said than done. So if you have any questions so far about this quick recap, then I'm sure Ramadevi, Pietro, and Shicheng will be happy to answer them. They are the leading experts on this topic. So moving on to the knot, the quiver, and the permutohedron. So this part I really like because it has a lot of visual input. So I get a lot of questions when I give this sort of talks. So I wanted to address this presentation by answering these questions. So can I obtain my quiver from a knot? How can I do it? So the simplest example is the on knot. So this corresponds to just one vertex quiver with no loops. Essentially, the generating series is completely agreed. So then the generating series for the colored Horn-Flippy polynomials of the trefoil knot, as Pietro already showed you, so he got ahead of me on this example, has this form, and you can rewrite this quotient of Q-Hammer symbols using this simple identity. This, in other words, is also a Q binomial identity, so nothing fancy going on. And once you substitute this identity here, you get a series in 3 variables, so 3 indices, and you can read out the form of the quiver from the exponents of the quadratic part of Q. So it's as simple as that. So if you give me the colored Horn-Flippy invariants, you can rewrite them and obtain a quiver matrix and the associated quiver directly from it. So it's always a way to obtain a quiver from a knot is to rewrite the Horn-Flippy polynomial in terms of dt generating series and deduce the quiver from the exponents. Can I find a knot for any quiver? What do you think? So I show you that the on knot has one vertex quiver for this generating series. The trefoil has a 3 node quivers, and the Hofling actually has a 4 node quiver. So one simple way to show that there is a lonely quiver without any knot is just to add a unit to any entry of this matrix. It won't longer reproduce the Horn-Flippy polynomials of the trefoil, but it's still a perfectly valid quiver generating series. So this matrix already shows that there are some quivers that cannot be associated to knots. So yeah, this is a simple example. So there are lonely quivers without knots. So this is a tricky question. Can 2 distinct knots have the same quiver? And this is a good question for the audience. What do you think?
Yes.
Yes? Anyone disagrees? Who gives more? Who gives less? Okay, so the answer is yes. But to be honest, during my PhD defense, I already knew the answer, but I panicked a little bit, so I forgot and I said no. So a very simple example are mutant knots. So they have the same colored Horn-Flippy polynomials. And what happened here is that, well, a quiver knows as much of your knot as the colored Horn-Flippy polynomials. So if the Horn-Flippy polynomials agree, then the quivers must agree. So it's an exercise for you to verify this.
That's because you are only on the subset of symmetric representations.
Yes, yes. So there's a very nice paper by Vivek and Satoshi Nawata and company claiming that a more refined version of these complexity polynomials, well, not truly refined, just what was it exactly? Mixed representations can distinguish mutant knots. So you can ask for more details. Is a quiver an invariant of the knot? Well, I didn't know how exactly the previous talks would phrase this, so they already gave the spoiler, and the spoiler is, well, there's no one-to-one correspondence between knots and quivers. The first case where you can see this is in the figure 8 knot. This is the matrix of the associated quiver for the figure 8. You can take these two off-diagonal elements and transpose them. So in this diagram, it's just a graph. It represents the starting node, so just a quiver matrix, and another node after the transposition, and we color the transposition, or we represent the transposition as an edge. Color will be, as you will see in a moment, to keep track of which entries are being transposed, but you can easily notice that two quivers will give the same partition function, and they are related by this very simple operation. So there's not a one-to-one correspondence. It can be precisely made into a theorem, which we prove, where it says that if you have two quivers, Q and Q tilde, and they both give exactly the same Humphrey-Petit generating series, then one way it could be is that these two are related by a simple transposition if they satisfy these constraints. You don't need to memorize the constraints, but the idea of the theorem is it's only a transposition of diagonal entries, so if they differ by 1 unit. So in this case, 0 and -1, they differ by 1 unit, and you can check that the rows and columns satisfy these identities, so then you're allowed to transpose it and get the same quiver generating series. But at first we thought it was just, well, maybe an isolated example. Who would expect this to go any further? But the 5-1 knot already had a slightly more intricate structure. So here you could do two types of transpositions, let's say the purple one between these two and the red one between these other two. As you can easily check, they differ by 1 unit. And these three matrices, once you put it into the quiver generating series, give you exactly the same colored Humphrey-Petit polynomials of the 5-1 knot. And the game goes on and it gets more complicated. So here I just do a matrix plot. I don't explicitly show the other entries that are not transposed. It's not important. So the idea is that these two entries differ by a unit. They can be transposed, so we draw an edge between them, and they represent these edges on this graph. So that's the importance of the color, to keep track. And you can already see that the number of quivers that can be associated to the 7-1 knot, it's well, more involved than for 3-1, 4-1, and so on. But it just keeps growing and growing and growing. So already for the non-afoil knot, so 9-1, you can see a pattern starting to emerge. Here, for example, you have these hexagons and these two edges. So these two edges can already appear in the 5-1 knot. Then you add these hexagons. Here, both hexagons and edges appear on the outer parts of this knot, of this graph. So obviously, it's quite complicated. We don't fully understand the reason why there's so many equivalent quivers, because each node in this graph represents an equivalent quiver for the same knot. And these edges, again, represent transpositions. But it's a very convoluted structure, which it just goes crazy. Already 11-1, it's even hard to draw. We've gone up very high for other knots, and even Mathematica at some point just spits out a number and says like, well, here's your graph, you plotted yourself too many nodes. So, short answer, no. There are more quivers for Q, for a typical knot, than viewers of this talk will have on YouTube. The next question, are the previous graphs Cayley graphs of some symmetry group acting on the quiver? Because we're just transposing entries, so it certainly feels like it should be a group. So there's a symmetry group. Well, it's not so straightforward, because you see there is an edge between these two quivers, but after you apply the purple transposition, because of the theorem that you need to satisfy certain constraints, you spoil them for the other quiver. So unfortunately, you cannot compose the purple and red transposition. So in other words, this does not form a group, because you cannot compose the operations. But each transposition by itself does form a Z2 group. So what we say is that locally we have a group structure, globally we do not. So that's why classifying or keeping track of these equivalent classes is not so trivial. So is Z2 the only local group present? Well, this is what the permutohedron enters this story. So the permutohedron graph is a geometrical representation of the permutation group. So hence the name permutohedron. So this is the simplest example. You have 1, 2, and on the other side you have 2, 1. Sorry for the low quality graphics. And this is the permutohedron of 3 elements. So you start here with 1, 2, 3, and then you go to 1, 3, 2. Here, a permutation is represented by an edge joining 2 different permutations. So, sorry, a transposition of neighboring elements is represented by an edge joining the permutations. There we go. And when you draw edges for all possible permutations, you get a hexagon. And you can go forward for 4 elements, and this is called a permutohedron pi4, which I really love it, so much so that I have a printed version which was given to me as a gift for my PhD defense. So every node represents a permutation, edges represent transposition of neighboring elements. So you can already probably guess the appearance of these permutohedron graphs in our symmetry graphs. So here we have one quiver associated to another by a transposition, then by another transposition. So they're jointing the two permutohedrons pi2 glued together on one edge. Here we have 2 hexagons glued at one middle point. So there are 2 permutohedrons joined at one particular point, and this represents again 2 Z2s joined at different edges, different vertices. And you can also check the same thing happens for this more complicated structure. They're just representing permutations of 4 elements and permutations of 5 elements. So it's pretty cool. That's why this was not a chalkboard talk, because I wouldn't be able to draw this by hand. But for those who must know, we tabulated the number of equivalent quivers. So symmetries, in this case, I mean the edges, so these coloring transpositions that we can perform on the quiver matrix. And equivalent quivers, the number of nodes. So for this list of simple knots, you can already see the huge numbers that they grow incredibly fast. So 6-3 was a bit of a headache, and it was the last one we could get. As I mentioned, Mathematica was not really willing to plot it. It took us a few days with the code we were running, but it's really hard. We so far do not have a whole grip on why there's so many, how to predict this number. So is Z2 the only local group? No. No, they actually have representations of Sn, and they're glued together in very complex ways. So those are the permutohedra. So if you want to find out more interpretation of these objects in terms of QB moves, I highly suggest you to go for Shicheng's talk at the end of this week. Is the knots-quivers correspondence proven for all knots? So spoiler alert, no. So this is a generalization of the knots-quivers correspondence. These two guys are what called thick knots, so thick homology knots, which they're Colore-Humphrey PT polynomials, satisfy some property called, do not satisfy a property called exponential growth hypothesis. So when you set Q to 1, they are not powers of the uncolored Humphrey PT polynomial. And this already sets them apart. The same knots-quivers correspondence that I was presenting you before no longer holds. And if you want to obtain a symmetric quiver representation, it's much more involved. And well, we can just say that there is a generalization to include these cases. So, in other words, we have proofs of the knots-quivers correspondence for various infinite families of knots, but there's not a general proof that tells you for any knot you will be able to find a symmetric quiver. But if you want to find out more about the generalization of the knots-quivers correspondence, you should go for Marcos Stosic's group and also giving a talk this Friday. So, moving on linking to infinity and beyond. So unlinking was already presented by Pietro, which I appreciate. So you're already familiar with this. Where do all the equivalent quivers of a given knot come from? That's a very fair question. So we realized that there is another operation defined on quiver symmetric quiver generating series, and that is called unlinking. So if you have a quiver Q and you pick two nodes A and B, you can define this operation where you add an extra node and then you subtract a unit of linking, so you remove one arrow. I'll show you a picture again how this looks, but the simple idea is that you increase the size of your quiver and the price you pay is to remove one unit of linking, but you get the same quiver generating series. That's why we call it a symmetry, because although you're using as an input a different quiver, a larger one, by construction, you still get exactly the same quiver generating series after you do a suitable change of variables of the extra formal variable. So the graphical representation is pretty intuitive. So if you have a quiver of two nodes, then you can remove this linking and add an extra node, so you get a quiver of three nodes. So that's why we literally called it unlinking. So the quiver matrices start from this 2 by 2, and you end up with this 3 by 3. So far so good. And in just one simple diagrammatic expression, the origin of these transpositions that we were allowed to do on the quiver matrix represented a knot is this. So this is a transposition between the off-diagonal entries AB and CD that differ by a unit. It's because if you unlink this equivalent quiver on the pair of nodes BC and you unlink the starting quiver on the pair of nodes AD, you get exactly the same unlinked quiver. So it's that this symmetry we were finding that you can associate many quivers to the same knot. It's in this view a degeneracy of this operation. So this is the diagrammatic expression, but below is a simple rule. If you apply unlinking on these nodes to this quiver, it's the same as if you apply unlinking on these other nodes of this equivalent quiver. So there is a symmetry operation acting entirely on these symmetric quivers. Don't really care about the knots. These calls for any quiver, whether it's associated to a knot or not, and the degeneracy of this operation manifests in the multitude of equivalent quivers for a given knot. So this diagram, it's only for one transposition. So the simplest case that I was telling you, or a permutohedron of pi 2. But certainly we saw that there are permutohedra with more transpositions. So what about them? So this is a very nice picture. Here, the nodes represent quivers, which all have the same, or equivalent quivers, which they all have the same quiver generating series. The arrows going up represent unlinking. You start with this, let's say, initial quiver. You unlinked on different pairs of nodes, and you get quivers with larger number of nodes. And if you continue unlinking in many ways, so in this web of unlinkings, at some point you realize that a permutohedron appears. So what is this in case the permutohedron is? Each of these orange nodes are related by a transposition of units. Or in other words, this is a way to start from an arbitrary quiver and obtain 6 equivalent quivers, all of the same size. Why? Because here, on each different level or slice, the quivers have different sizes. But at this size, we can already see the appearance of the pi 2 quiver. And you can do so for pi 3, pi 4, so on, but the figures are harder to plot. So yes, all the permutohedra arise from this degeneracy of unlinking, just more complicated ways of unlinking. So how many quivers can we associate to a given knot? So this also relates to other work we did, because there's nothing stopping us really from unlinking as many times as we want, is it? So if we start with a trefoil knot, we can unlink this element, we can unlink this element, and we can apply unlinking twice here. And voila, what we got is a diagonal block matrix here, and here extra nodes that each of them will have higher powers in X. But this part already, it's diagonal. So the quiver generating series up to certain order just factorizes. So this is what we call the infinite diagonal quivers, but this is just the first step you need to go. Then if you want to have, this will give you the first order DT invariants. If you want to obtain the second order, then you need to unlink all these pieces here. You will add more columns, but then the quiver generating series up to second order would factorize, and on the diagonal you will get exactly the corresponding DT numbers. Oh, but the generating series for a quiver of a single node. Okay, yeah. So yes, the resulting quiver series can be repacked as into this infinite product form. Oh, sorry. Okay, so the moral of the story at the end of the day is that we found a large set of quivers associated to the same knot. There is a very intricate web of dualities, which is labeled by permutohedra, for where for each node we have many quivers. And the permutohedra are a consequence of unlinking. So this appear of properties of the symmetric quivers themselves. We can unlink infinitely many times, and in this way, at the infinity level, we get a completely factorized quiver generating series, which is again easier said than done, because you get a very, very large matrix as you go along, and you get to get to the fourth order DT invariants, then the number of unlinkings you will need to perform just grows incredibly fast. So it's not so much as a easy way to compute this DT invariance, but rather as a proof of principle that this infinite product form that we showed can arise naturally as well from unlinking. So what do we want to go from here? So one question I personally would like to understand is what is the geometrical interpretation of a quiver associated to a knot? Can we read it from a knot diagram or from the knot complement? Can we have an explicit formula for the numbers of equivalent quivers? So if you give me a knot, can I use a simple formula to tell you how many quivers map to the same knot? Are there any other equivalent quivers that we're not aware of that may even come from unlinking? We're not 100% sure. And yeah, like I said, how these unlinkings, equivalent quivers, are viewed directly from the knot diagram. So they're very abstractly defined. You first need to compute an infinite sequence of polynomials mapped to quiver representation theory, and there these things make sense, but knots do not need all that to be studied. So maybe there is a way to import back all this knowledge of quiver generating series to knots, and it will be very interesting to see. So, thank you very much.
Questions?
Can you go back to the third diagram, like the third graph of this? This one, the next one. Yes. I think because okay, I can see the permutohedron like the hexagons and the big ones, but there is like this square thing between the big like.
Yeah.
What is this?
So this is the first instance where you can actually have commutativity. So remember that these transpositions appear at different places on the quiver matrix. So in the end, if these transpositions act on very different pairs of nodes, meaning that do not break each other's constraints, then you are allowed to act on them, to compose them, or act one after the other. So you can see here there's this red, red, purple, purple. So for these transpositions in particular, so red and purple, you can see that they are very far away from each other on this matrix. So when you transpose these elements, you don't affect the conditions on this, so you can still carry out this transposition.
Okay.
But the more involved question is, and we still really cannot get the heads around it, these antennas we call, because they're just gluing at very random places, and it's very hard to understand them, because these large structures, as we saw, the permutohedron, more or less we have formulas for them, but the appearance of these guys, it's so far a mystery.
You also said about examples where the correspondence fails. Can you show again this slide?
Ah, for sure. It doesn't fail. It doesn't work in its current form. It doesn't have the... So the correspondence arose from... where is this formula? Let's say rewriting everything into this type of series. But for these knots, the mutant pairs. Did I pass?
No, you want to take knots.
Yes. For this, not mutant pairs. So these stick knots, which do not satisfy the exponential growth hypothesis. There's a paper by Stosic from this year, actually, just a few months ago, where he found generalization of this quivers generating series, which can match this the Color-Humphrey PT polynomials of these knots. So this is the key thing. So the quiver generating series, as I show you, cannot reproduce this always reproduce this behavior. So when you set q to 1, all the remaining n elements of the sequence are just powers of the first one. So that's its exponential growth. These knots are the first examples that do not satisfy that behavior. So they cannot have a quiver generating series as we know. So there's a generalized knots-quivers.
Maybe let me comment on what you say, because I would phrase it in some slightly different way. It's related to the paper we wrote with Pietro and Tobias Ekholm. And in fact, if you consider knot-quiver correspondence for these kind of knots, it can be written in a quiver form. However, the crucial difference is that in this change of variables, you have potentially higher powers of x. So what Elder is saying, it is totally true when you fix it to 1. Then you cannot write it in this quiver form. And this version with 1 was initially proposed by us. But then in this paper with Pietro and Tobias, we noticed that some homologies grow too fast, so we need to add more quiver nodes as generators, and some of these quiver nodes appear at the second level in the homology. So this is why we need higher powers here. And in these new results from Marco, they're consistent with this. So this is fine, although there are more subtleties when we introduce also t variable, the homological grading. And then it is still open question, and new paper by Marco, probably he will talk about it. Give some new hints, but we still don't understand it fully.
So what I remember reading is, okay, besides this modification to the change of variables, you also need to add extra factors inside the quiver series. Oh, so no longer the quiver series, because it's not necessarily associated to the DT invariants, but you need to add extra factors. And then he was able, Marco, to match it to the generating series of these knots from what I read in his article.
I think we should refer to him. My understanding is that this is what you are saying applies to t variable as well.
Okay. Okay.
But we should wait to him, and he will tell us best. Any other questions?
Does the permutohedron as a physical interpretation, maybe in the context of the in-theory origin of the knots-quiver correspondence?
To put it in a few words, so these quivers, the symmetric quivers, they arise as mixed Chern-Simons levels on 3D n equal 2 theories. This just means that different Chern-Simons levels give you exactly the same supersymmetric index, in a few words. But as I show you, you can always increase the number of mixed Chern-Simons levels and get the same supersymmetric index. But the idea is that the minimal number of nodes that a quiver has to have for a given knot, or what we call the minimal quivers, you cannot remove more nodes in this case. So this is the minimum number that you need for a given knot. So 3 is the minimal for the trefoil, 5 is the minimal for the figure 8, but you can always increase nodes. But apparently for 1 or figure 8, you can have 2 quivers which have the same number of nodes, but explicitly different. So it would be like 2 different mixed Chern-Simons levels of these 3D theories, with giving you exactly the same supersymmetric index.
Other questions? If not, let's thank Elder again.